Why was the chord upset with the tangent after the race? Because they came in secant. Get it? Secant, second. So we're looking at some angles created with tangents and secants in your notes. So what happens? In particular, we're looking at an angle where the vertex is at the point of tangency. So you see how the tangent here is making a right angle. In this example, I'm saying that arc DE, which is right here, is 82 degrees. So I put the 82 there. I want to find, to start, the measure of angle DBE. Now I'm going to actually want this entire angle, but I'm going to start with what I know. I'm starting with angle DBE because it's an inscribed angle, and you can see that this angle is just half the measure of that arc. So I take 82 divided by 2, and I get 41 degrees for this angle. Well, if I want this whole angle at DBC, I know that this is a right angle already because this is tangent. And I just add the 41 to the 90, and I get 131. This will also, so I've got 131 here. Let me go ahead and find the the arc measure right here. Your notes might have a different notation, but it should be arc DEB. I put 3 letters up here because this arc is more than 180 degrees. So it's D through E all the way to B. Well, I know that this arc right here is half of a circle, so it's 180. And I just add that to the 82, and that gives me 262 degrees. Well, if I compare the measure of this angle, we found out it was 131 degrees. With the measure of the arc, it's 262 degrees. So the angle is half of the measure of the arc. Now, will that be true if the angle is actually inside? So let's say I had an acute angle instead of an obtuse angle. Well, we'll play with some angles here at this little applet, and we'll find out. Okay, so I have this little applet, which you can get to from the URL in your notes. And if you move this point D, you can see the relationship between the intercepted arc, which is this red curve here, and the angle. BC is tangent to the circle, meaning if I connected A with B, I would have the radius would be perpendicular to B at this point of tangency. So, and then BD is a secant. So as I move the point, you can see, I'll try to pick it so it's a nice number. And so 232, half of that is about 116. As I come down, say when it gets close to, I won't quite get 180 degrees. There we go. Oh, that was pretty good. So there's 180 degrees, and you can see that the angle here is 90 degrees, which makes sense because this would be perpendicular to the radius right there. Sliding it in further, it gets smaller and smaller, but this is still always half of that. So here you go. Let's say it's about 62 degrees. There it is, 31. Whether it's acute, right, or obtuse, that relationship stays the same. This angle here, which is in green, is always half of the intercepted arc. So what relationship did you notice? The angle created by a secant and a tangent at the point of tangency is always half of the intercepted arc. So if this angle is the one I'm looking for, I'll call it angle 1. And the arc we'll just call x degrees. Then the measure of this angle is x degrees divided by 2. So it's a lot like our inscribed angle relationship. So now we're going to take a look at intersecting chords. And the first thing I'm going to do is find measure DEB. Why am I doing that? Well, if I put a line here, you can see that that's an inscribed angle, and I know what to do with those. So I can just take half of 29.4 degrees, and that would be 14.7 degrees. Now, I'm also going to go ahead and find angle CBE, which is this angle right here. And you can see I have the arc opposite there, 50.2 degrees. So it'll be half of that, which is 25.1. Then I'm going to use the exterior angle theorem. Do you see the triangle, BFE? So I'm going to find angle DFB right there by saying it is the sum of the two remote interior angles. We did that in the fall semester. So those are the two angles we're going to add together. And I end up getting, in this case, I should have added it, 39.8 degrees. So how does that compare to the measure of angle DB and CE? Well, hopefully you'll notice that it's just half of their sum, or the average. So let's go ahead and explore this and see if this holds for any type of chords that we have, whether it's just true for that specific example or in general. All right, here I have two chords, and I can move the points B, C, and D, so you can adjust them any way you want. And you can see a relationship here. I have the arc BD is 133.5 degrees. Arc CE is 74.2. Then I took the average of the two arcs by adding them together and dividing by 2. Well, here on this diagram, you can see the measure of this angle created by the two chords that's opposite these two here. So it matches. If I take the average of these two red arcs, then I get the angle here. And by the way, this angle is a vertical angle, so it'll also match. And it doesn't matter how you set up these chords. They could be intersecting almost at one end, 43.9, 43.9. You could have it almost in the middle. It still works, 74 and 74. So the cool relationship that you see here is that this angle created by the two chords is the average of the two arcs. And how do you find the average of the two arcs? You add the measure of arc BD here and the measure of arc EC and then divide by 2. So what relationship did you notice? Well, the angle created by two chords or secants is always the average of the intercepted arcs. So you add the two arcs and divide by 2. So here I have a picture, and this is what will be on your chart that we made for you. Here's the arc here, x degrees and y degrees. If I'm looking for the measure of angle 1, it's going to be x plus y all over 2. By the way, the measure of angle 2 will be the same because these are vertical angles. So in reflection, how is the first problem that we did similar to inscribed angles? We used inscribed angles actually for all of these problems. How can you find the measure of an angle with a tangent and a secant when the vertex is at the point of tangency? Hopefully you're noticing that it's really very similar to inscribed angles. Where's the vertex of an angle created by two chords? You should have noticed that the vertex that created the angles was inside of the circle. How can you find the measure of the angles created by two chords in a circle? Well, that's the formula when two chords intersect. Hopefully you remember, you just wrote it down.